Greetings everyone, we're from Group A and this is a video presentation for ECC3120 Signals and Systems project. So first off, I would like to introduce my group members. So my group consists of 4 members. First one is Nur Ain, which is me, and then we have Zal Hazmi, Nurul Afifah, and also Adriana Nabilah. And for today's presentation, we would like to focus on part B, but before that, our title for our project is Analog Filter Evaluation, and for this project we have to choose one active filter and also one passive filter, and we have to describe, we have to find out the transfer function and also solution. So this presentation will be going like this. Okay, so first the presentation will start with active filters simulation and also brief introduction. I'll be doing the introduction, also Zal will be doing the simulation, and then Afifah will go with the brief introduction for passive filters, and Adriana will do the simulation for passive filters. So what is actually low-pass filter? So low-pass filter is filter that passes signals with a frequency lower than particular cut-off frequency and attenuates all frequency higher than the cut-off range. And that was active low-pass filter. That was low-pass filter. But what is exactly active low-pass filter? Active low-pass filter is the filter that I've mentioned just now, but it is being built. It is built, or the configuration is using op-amp as the components to build it, and the function is to improve the performance and predictability in such a low cost. As for theoretical calculation, we have things to be calculated, which are capacitive reactance, phase shift, cut-off frequency, and also transfer function. So these are the values that will be used in order to calculate all these components. Okay, we have R1 1 kilo ohm, same goes to R2 1 kilo ohm, and then capacity 0.01 microfarad, and also frequency 15 kilohertz. As for capacitive reactance, as you can see, the formula given here is X is equal to 1 over 2 pi FC, which when we use all the values given here, we'll get 1061.33 Hz. And as for phase shift, this is the formula, and then after we use the values that given here, phase shift will get is 43.30 degree. As for cut-off frequency, this is the formula, which is 1 over 2 pi R2C. And after using all the values given also, the cut-off frequency is 15.915 kHz. As for transfer function, the final formula given here is R2 over R1 over R2CS plus 1, and the inputting of the values given will be getting transfer function. And then all passive presentation result for simulation.
Okay, now I will proceed with multi-sim simulation. So this is the circuit that we constructed in multi-sim software. The circuit that was chosen for the active low-pass filter is an inverting amplifier filter. The filter consists of op-amp, 2 resistors, and 1 capacitor. The value of resistor is 1 kilo ohm, and the value of capacitor is 0.01 microfarad. The function generator that was used as a power source in the circuit was set into 15,000 kHz. To get the simulation graph, we connected the oscilloscope and bot plotter. So this is the result for the oscilloscope, as we can see here. And now this is the result for bot plotter. As we can see in figure 3, at negative 3 dB, the frequency that we get, or we call it as cut-off frequency, is 15.638 kHz. From the theoretical value from the calculation above, the actual value of cut-off frequency that we get is 15.915 kHz. So the difference between actual value and the multi-sim simulation is 0.277 Hz. From this difference, we calculate the error rate, which is the theoretical value minus multi-sim value over the theoretical value times with 100. So we get 1.74% the error rate. Now we'll move move to the next quarter. For the phase shift, as we can see here, at 45 degree, we get the frequency is 987.797 kilohertz. Now we move to the octave simulation. For the octave simulation, based on the code above as in figure 5, it is a code to simulate the board diagram in octave simulation. It is to generate the board diagram based on the transfer function value. As you can see here, this is the code to generate the transfer function, and then we include the value of resistor, which is 1000 ohm, and the value of capacitor, which is 0.01 microfarad. So this is the transfer function formula that we get from the calculation above. So this is the answer for our transfer function, which is negative 13.717. So this is the transfer function that we get, which is 1 over 1 times 10 minus 5 s plus 1. And this is the board diagram that was generated from octave simulation. I think that's all from me.
My name is Nurul Afifah and I will be presenting passive high-pass filter theoretically. Okay, so passive elements such as resistor, inductor and capacitor are the elements that make up a passive filter circuit. It consists of a combination of resistor and capacitor or resistor and inductor. Passive filter circuit does not use any amplification or external power source. The RC filter consists of a capacitor which is connected in series with a resistor. The capacitor acts as an open switch because it offers high reactance for the signal with a frequency lower than the cut-off frequency. So this here is the RC circuit. The cut-off frequency is a frequency that draws a boundary between pass band and stop band. If the signal frequency is higher than the cut-off frequency in a high-pass filter, it will allow the signal to pass. But if it's lower than the cut-off frequency, the signal will attenuate. The frequency response of the filter circuit can be plotted using the transfer function. So this is the theoretical calculation. The resistance used in the experiment is 1 kilo ohm and the capacitance is 0.01 microfarad. So this is the calculation for reactance, and we got 1.061 kilo ohm. This is the transfer function, and this is the cutoff frequency, and this is the phase shift.
I will be presenting the simulation of high-pass passive filter using multisim and auto software. The high-pass passive filter circuit consists of 1 volt AC power voltage supply with the frequency of 15 kHz, 1 kilo ohm resistor and 0.01 microfarad capacitor. The frequency response of the circuit is observed by using the Bode plotter component. The sine waves can be observed on the oscilloscope. The magnitude mode of the Bode plot shows that the cut-off frequency is 15.955 kHz at negative 3 dB. Meanwhile, the phase angle of 45 degrees and the cut-off frequency is 15.95 kHz can be observed at the face of the Bode plot. Based on the Bode plot, there is a slight difference in the theoretical and multisim experimental values of the cut-off frequency. The error obtained is 0.2513. Moving on with the gain of the circuit. The gain is calculated using the formula of 20 log V out over V in. By substituting the values of V out and V in the formula, we can get the gain of the circuit is negative 3.26 decibel. Next, the octave simulation. The frequency response of the transfer function is observed by using this command: system equals to TF bracket 10, comma 1 and 100 exponent 3. Transfer function of the high-pass passive filter is S over S plus 1 over RC, in which the resistance value is 1 kilo ohm while the capacitance value is 0.01 microfarad. The boot plot of the transfer function can be plotted by using this boot command. The output of the code above is the magnitude and phase plot. By comparing the outputs of multisim and Octave software, it can be deduced that the shape of the boot plots are similar. However, the shape of the boot plot using the Octave is more accurate as it is obtained by using transfer function. The output of the multisim software is achieved by constructing a circuit which must consider the circuit elements that may affect the overall output. I think that is all for the simulation part.